Hey everyone, ever crack open a piece of really high-tech gear like a radar system and wonder what's going on inside? You might expect a bunch of wires, but for microwaves, it's totally different. It's more like a set of incredibly precise plumbing for invisible energy. So today, we're going to do something cool. We're going to build a virtual microwave system right here, from the ground up, piece by piece, so you can see exactly how this invisible plumbing really works. All right, let's get into it. Here's the game plan for our little project today. First, we'll lay down the highway for our signal. Then we need to actually create some traffic to run on it. After that, we'll figure out how to direct that traffic, measure its flow, and finally, make sure it all comes to a nice, safe stop at the end of the line. Okay, first things first. Before we can even think about generating a signal, we need a path for it to travel down. And believe me, this isn't your average copper cable. This is something way, way cooler. Say hello to the rectangular waveguide. And yeah, it is literally just a hollow metal pipe. But here's the magic. Unlike a normal wire where electricity flows through the metal, microwaves travel through the empty space inside the pipe. They actually bounce off the inner walls, zigzagging their way down the line. It's an incredibly precise, high-tech pipeline built just for waves. So you might be wondering, why go through all this trouble with a hollow pipe? Well, because a waveguide is an absolute tank. It can handle insane amounts of power without breaking a sweat. We're talking the kind of power a massive radar transmitter needs to see for hundreds of miles. Plus, it has almost no signal loss, which is absolutely critical when you're trying to pick up a whisper-faint signal from a satellite deep in space. It is, without a doubt, the heavy-duty superhighway of the microwave world. All right, our highway is officially open for business. But a highway with no cars is pretty useless, right? So now we need to create the traffic, the microwave signal itself. We need an engine, something that can generate these super high-frequency waves. And that's the million-dollar question, isn't it? You can't just hook up a couple of AA batteries and call it a day. For this job, you need a very special piece of equipment, a real legend in microwave labs. And here it is, the Klystron tube. Now, I know it looks like some kind of retro vacuum tube from an old sci-fi movie, but this thing is the heart of our system. It's a powerful oscillator that acts as our engine, purpose-built to create the high-power, high-frequency signals that are about to go screaming down our waveguide. So how does this thing actually work? Well, the traffic analogy here is just perfect. The Klystron starts with a steady, kind of boring stream of electrons, like cars all leaving a traffic light one by one. But then, it uses electric fields to mess with their speed, speeding some up, slowing others down. As they travel down the tube, the fast ones catch up to the slow ones, and they naturally form these dense, powerful packets, or bunches. And when those super dense bunches of electrons zip past that final catcher cavity, boom! They induce a massive microwave signal. It's an incredible way to turn a simple, steady flow into a powerful, pulsing wave. Okay, we have our highway. We have our signal roaring out of the engine. But, in any real system, you can't just have energy going in one straight line. You need intersections, on-ramps, one-way streets. You need traffic control. And that's where our next couple of components come in. Think of them as the traffic cops for our waves. Now this is a microwave circulator, and it is just one of the cleverest devices ever. The absolute best way to think about it is as a traffic roundabout for waves. Energy comes in one port, but it is forced to leave through the very next one in the circle. It absolutely cannot go backward, and it can't skip an exit. It has to follow the rules. So let's walk through it. Let's say our signal from the Klystron comes in right here at port 1. The special magnetic fields inside this device force that signal to turn and exit only at port 2. It literally has no other choice. Okay, now what if a signal comes back into port 2? Maybe it's a reflection from whatever is down the line. Well, it can't go back the way it came to port 1. Nope, the roundabout rule is in effect. It's forced to take the next exit, which is port 3. And, you guessed it, to complete the loop, any signal that happens to enter at port 3 gets sent right back around to port 1. This super strict one-way flow is absolutely essential for things like radar, where you need to send a powerful pulse out an antenna and then listen for a tiny echo coming back through that same antenna, all without the two signals crashing into each other. But what if you don't need a whole roundabout? What if you just need a simple one-way street? Well, then you use an isolator. It's really just a clever trick. It's a circulator where that third port is connected to a material that just absorbs all the energy, like a dead end. So a signal can go from port 1 to port 2 just fine, but anything that tries to come back, any reflection, gets shunted off to that dead-end third port and just disappears. It's the perfect one-way valve, and it's how we protect our expensive klystron from any stray energy that might bounce back and cause damage. So our signal is being generated, it's being protected, its flow is being controlled, but it's still totally invisible. How in the world do we actually see it? How do we measure what it's doing? For that, we're going to need a few special tools. You see, measuring a microwave signal is a really delicate dance. You basically have to stick a tiny little antenna called a probe right into the waveguide to get a sample of the energy. But as this quote points out, the trick is to do it in a way that doesn't mess up the very signal you're trying to measure. It's all about grabbing just enough information to see what's going on without causing a big disruption in the flow. And these are two main tools for the job. Think of the tunable probe like a technician walking along the highway with a handheld scanner. It can actually slide up and down the waveguide to check for things like impedance, which is basically how smooth the energy flow is, and it can pinpoint trouble spots. The detector mount, on the other hand, is like a permanent traffic camera bolted to an overpass. It stays in one spot, and its job is to constantly measure the signal's strength or to decode the information that the signal is carrying. Okay, we are so close. We've built almost our entire system. We're generating a signal, we're directing it, we're measuring it. But what happens at the very, very end of the line? We can't just let the waveguide stop. The energy would hit a dead end like a brick wall, causing a massive reflection, a chaotic multi-car pileup that would send all that energy screaming back the way it came. That would be a disaster. The solution is this elegant little component, the matched termination, or sometimes just called a load. Its one and only job in life is to be the perfect energy sponge. It is designed to absorb 100% of the microwave energy that hits it, making absolutely sure that nothing, and I mean nothing, gets reflected back into our system. So how does it pull this off? It gives the wave a soft landing. If you look inside, there's a tapered, pointy piece of material that loves to absorb energy, like graphite. This conical shape means the wave doesn't hit an abrupt wall. It eases into the material gradually. And as it travels down that taper, its energy is just smoothly soaked up and safely turned into a tiny, tiny amount of heat. It's the most peaceful, perfect end to the signal's journey. So there you have it, from our klystron engine, down the waveguide highway, through all our traffic controls, and all the way to the matched termination at the end of the road. We've just built a complete, working microwave system. But that leaves us with one last big question. We've seen all these individual lab components, but how does this invisible plumbing scale up to power the incredible technology that runs our entire world? From the weather radar you check on your phone to the satellites beaming down your TV signal, that's something to think about.